Hey everybody, what is going on? And welcome to the third tutorial of Q Learning part series. So in the last tutorial, we had just left out by creating the Q table, which was initialized using the np.random function uh, and the uniform, which sort of creates a Q table of random values. And initially, these random values don't matter, as we have discussed before. Now we have to figure out a way to like make the agent fine tune that Q table. So if we see that Q table here, this is our Q table which we have created, and these are a bunch of random values. These are by random Q values, right? So now we have to make the agent update these Q tables, in sort of way that makes sense to the agent in achieving the goal. In our case, reaching to the flag, right? So that is what we are going to be doing in this tutorial. Okay, so how do we make um, the agent update the Q table? So right off the bat, let's just start off by defining few constants, right? Let me explain while I define them. So first one is learning rate, LEARNING rate, which um, is 0.1. Right, next is the discount factor. Discount, we'll set it to 0.95. Right, and then episodes. So episodes, we'll set it to, let's just say, for 25,000 episodes. So what are all these constants? So the first of all, learning rate. If you are sort of familiar with different optimization functions like RMS prop and all of those kind of all those functions, they take in something called as learning rate. So what is this learning rate? So you can think of learning rate to be a value which sort of tells the agent as to how fast he has to learn with respect to time, right? So how do we say that? So how fast he is going to learn uh, with respect to time. We have to keep this minimal. This is a value which goes between 0 to 1. So uh, we have to keep the value minimal, because if we, let's say, if we keep the learning rate to be 10, or I mean, in the sense like 10%, or let's say even 95%, what is going to happen is the agent might sort of learn something which makes no sense, right? In the sense that he would just learn to uh, you know just reach the goal, right? So if he finds any obstacle in between, he will not be able to figure that out, because his aim is only to reach that goal. And if we say a learning rate of 0.95, so he just wants to figure it out very quickly, and he will sort of neglect all the other essential attributes that are to be considered, right? So uh, those kind of things might happen if we keep the learning rate more. So something of you can think of in the classical machine learning, if I have to say, something like overfitting, so to say, so something of that sort. Right, and next is the discount factor. Discount factor, so if to put it in terms, it is something like, it's a measure of how much we care about the future reward, right, rather than the immediate reward. Something of since we are talking about episodes, it's like how much we care about 100 episodes in the future rather than the next episode, which sort of makes sense, because in this you have it sort of emerges, right? So when the agent is trying to learn, the queue values in the queue table starts updating and start of emerges not right out of the bat. I mean, so to say, not right immediately, but after few iterations, right? So that's what we are trying to portray here. So this is the measure of how much we care about the future rather than the immediate reward. So we want the future reward to be really good, if not the immediate reward, right? Which makes sense because after learning multiple times, at least you have to sort of become good, right? If you started off how you are, and even after like 100 200 iterations, if you're still the same, maybe it doesn't make sense, right? So we have to sort of specify in sense that how much we care about the future, future reward rather than the next immediate reward, right? So that is discount factor. And the episodes, nothing more clear. It's something, it's just like epochs. So how many times you want to sort of let the agent explore the environment in order to have a good emerging queue table, so to say. Now, as of this, these queue tables makes no sense to the agent, so we have to make the agent explore and exploit the environment in order such that these queue tables can be updated, right? And that happens over a period of time, and we have selected for 25,000 times. So those are called as episodes in terms of queue learning. But the nearest the thing which you could relate to is the epoch in the classical machine learning, right? So these are a few constants that we denoted. And the next thing is creating the queue table, I mean, sorry, the creating yeah, now we have created the queue table, but how do we update the queue values is the next question, right? So how do we update the queue values? So we have a formula, so to say, which um, exactly denotes the exact formula that has to be laid out. So let me just show you the formula. So as you can see here, the new state q new of this depicts that q new of the given state, and the I mean q new of the state and the action at that particular time t is equal to 1 minus alpha denotes learning rate, so 1 minus the alpha. So as we said, the learning rate is, as we specified, 0.1, right? So that is what it is. So 1 minus alpha times the old q value, or so to say the present q value, right? So we are trying to predict the new q value. So that is the new q value is equal to 1 minus alpha times the present q value plus the learning rate, right, times the reward for that particular particular state, also with the discount factor, and the maximum q value at that particular instant of time, right? So that is, I know it is a lot of information to throw at you in one shot, but when we code this out, I think it's going to make a lot more sense than just seeing the bare formula right here. But essentially, in the nutshell, this is what it is. So it's 1 minus the learning rate times the present q value plus the learning rate times the reward plus the discount factor, and the max of the q value. So let's get back to the Python, right? So now how do we we saw as we saw a bunch of new variables, right? So they are we have figured out the learning rate, we have figured out the discount factor, right? So we know reward, right? So how do we create and make this formula uh, uh, you know to be working, right? So how do we do that is the question. So now, since we have defined all of these uh, you know constant values, we should be able to sort of make sense of that formula now. And as we saw, you know let me just go ahead and print out you know the so as you can see right off the bat, let's okay, cool. So these are all, I'm trying to print out the observation. So these are all the observation, right? So that is what we are doing. So observation is something like the state, at what is the state of the agent at a given time. So that is what it means. So we have to sort of use this. But if you can see, we are sort of getting decimal places up to, I think, about 4 decimal places, which is too granular if you think about it. And right off the bat, if we start filling our queue table with such granularity, it's definitely going to run out of storage, and it's going to overpopulate. And we really don't require such granularity, in a sense that maybe we can just get away with 1 decimal point, right? So we don't really need so many decimal places. So in keeping that in mind, we have to figure out a way to sort of only take the necessary values and not populate our queue table unnecessarily with huge values which doesn't even make sense to the agent. So so how do we get that working? So we can sort of develop a create a function. Let's create a function which will get the the state, get the state, get state. So get state, so which takes in the state, and it basically, let's say it a discrete discrete state equal to the state given minus the low of the environment, right? So observation space dot low, divided by the discrete window size. So discrete observation space window size. So if you can get what I'm doing here, is I'm trying to create a discrete state. I think this is not going to make sense right now. Just let me just finish this. I'm going to return a tuple a tuple of the discrete state, um, you know as type as np dot integer. So I think now it's going to make much more sense. So right, we told that we don't want such granularity, right? So it really makes no sense for the agent to give such huge q values and tell that q agent to figure it out. So what we are trying to do is we'll take that state wherever the agent is in, that is these values, right? Minus it with the low of our, if we minus it with the low, right? So yeah, so this is the low, right? So this is the low. So we take that particular state where the agent isn't at that point of time, and then negate it, or subtract it with that, with the low of that particular environment, and divide it by our the OS size which we have created here. So if you want, I can print that out. So which will have uh, okay, that's okay. So I think but anyway, for the sake of understanding purposes, uh, this is, it returns the high minus low times the discrete, so 20 by 20. So if you want, let me just read on the console, and let me just copy and paste few items so that we get a better understanding of what we are trying to do. And now if I print discrete within OSI, so we are trying to divide it by this. So in a sense that if you remember from the previous tutorial, we are trying to create 20 discrete values, and which have the ranges, a decimal 09 till decimal 007. So if we divide this by that factor and convert it to an integer, np dot integer, I think this will make much more sense in order to fill up the q values, so to say. So right, so this is somewhat like a helper function which will return an integer, which is a tuple basically. And now I think we are in a good shape to sort of initialize uh, the discrete state. So discrete discrete state, oops, is equal to get state, and I'm going to pass in env dot reset. So if I say env dot reset, so let me just show you uh, env dot reset. So this returns an array of lists of shape 2, right? So of length 2 rather. So this is the start of state where the agent starts off, right? So we are trying to reset the environment completely and start off new. So that will be our first state. So that is what we are saying. So get the first state, right? Once we get the first state, now we can start off, go ahead and start updating our queue table. Hope that makes sense, right? So and then once we get the queue, the first state, how do we select the queue values? I mean, and what basis do we perform the action? If you remember from the the first or second, I think from the first tutorial, we said that we will take that particular column whichever has the highest q value, right? So that means to say we will perform that action which has the highest q value. So in a sense that in this case, in this particular scenario, this has the highest q value, so we are going to perform the action 1, right? So that is what we are going to do. And we can do that using the numpy dot the np dot argmax, which will help us to select the it will help us to select that particular column which has the highest value of that row, right? So hope it makes sense. So we have to get the argmax of the q table of the discrete state. So I hope that makes sense. So what we are essentially trying to do is we are trying to perform that particular action where we get the state of that discrete state. So that way we can start updating our q table, and hopefully it will emerge out to become a proper sensible q table. And then how do we perform the new how do we get the new state? So we get the new state, this observation is the one which is somewhat which will return to us the new state. So we are going to say new discrete new discrete new discrete state would be equal to get state of what of observation. So observation, as we saw earlier, it returned the particular state of the agent in the environment at that particular point of time. So once we start getting that, we can pass it to our helper function, which will return an integer value of sensible integer value, and then we can start updating the queue table. Right, so now how do we update the queue table? Now let me just comment this. I don't think we need anything any yeah. So now if not done, right? So if not done, and this also yeah, so this returns done. And if not done, so that means to say if we have not achieved our goal, so what we are trying to do here is, let's just look back at our the the formula, and let's just make sense of that. I'm just going to keep this for reference, so such that we can see and then code so that it makes sense to you guys. Okay, fair enough. So okay, uh, if not done, so what we are trying to do, if not done, that means to say if we have not achieved our goal, that is to reach the flag, we have to get you know we have to sort of do this operation, right? So we have not achieved it, so we are trying to update our queue table until we keep on achieving. I mean, until we achieve and reach our goal, we have to update the queue table. So based on the queue table, the agent takes actions and then perform those actions. So right, so if we have not achieved the goal, let's start off by getting the maximum value. So maximum queue value, if you can see here, it's a maximum queue value of the state plus one comma action. So it's a future value somewhat saying. So let's say max future, future future q val is equal to, it's a maximum of a particular discrete state, right? So we can just say np dot max of the new discrete state. Hope it makes sense. And of course we have to cast this as a list. Oops. So what we are trying to do here is we have to get the maximum future value, which is this, this value here, like this part of the formula, where it sort of gives us the maximum of the new state, right? New state. So new discrete states. That is what we are doing. And then we also want the current state, that is the present state, because we are trying to find out the new state, so we also want the present state. So how do we get the present state? The present state, how do we get the present state is just the current q value, or I could, current q val is equal to the q table of the discrete state plus the action. So hope that makes sense. So how do the current q value, how do we get the current q value? So the current q value is just that particular, the discrete state, that is the state and the action of that state. So that's what we are essentially doing here. So we are trying to get the value of the discrete state along with the actions. So that particular state along with the actions. Hope it makes sense, right? And then I think we can just code, make our new q value. So since we have all the necessary values, we can just create a new q value. New q val is equal to, as the formula says, 1 minus the learning rate, 1 minus the learning rate times the current q value, right? So plus the learning rate, right? uh, times the reward. So where are we getting our reward from? The reward is returned to us by the gym, from the env step. So the steps that is taken, and it immediately returns to us the reward. So reward plus the discount factor times the max future q val. Now I think it makes more sense that we have gone through the entire formula, and we have sort of created our future qval, which is nothing but the new state, new discrete state, right? And then the current qval, which is the present state, which we get it returned, right? And the new qval is nothing but just deploying the formula as it is. So we have all the necessary values, and all we have to do is we just have to update it. That's it, right? So how do we update it? Now we have created a new q value table, and we just have to say We just have to update our present queue table. So queue table of that particular discrete state, right, plus the actions, oops, okay, the actions must be equal to the new queue val, right? So it makes sense now. So whatever we get from the new queue val, uh, that we are just setting it to the present queue, the queue table at that state. So sort of we are updating the queue table as it goes. Now if this is until the simulations takes place, right? So this is until our agent has reaches the goal, right? Once we reaches the goal, I mean once the agent reach the goal, what are we going to do? So we can just say elif, oops, elif elif the observation of 0, you know is, yeah, just in case you're wondering what is the observation of 0, let me just print that out as well. Okay, sorry about that. So till where have we? Yeah, I think I'll take this out and make this full screen. And now that we have better, we can see it better. Okay, okay, fair enough. So how do we get the observation? So observation is returned to us by the env step. So I'm just gonna go ahead and copy and paste this, because why not? Yeah, so okay, so I'm just gonna copy and paste this. So how do we get, and so to know what exactly the observation of 0 gives us, I'm just gonna do that. Okay, great. And I think I can start observation. Yeah, so observation of 0 would give us that, and if it is greater, what I'm trying to say is, if that particular observation of 0 is greater or equal to our env dot, the goal, oops, goal underscore, goal position, posi ti posi tion, ooh, tion. Sorry about that. So if the observation of 0, so env dot goal position, so what exactly is that? Env dot goal underscore position. So if we print that out, that is going to give us a 0.5, right? So if that observation is greater than or equal to our goal position, so meaning that we have reached our goal, that is we have achieved our goal, right? So then what we do is we can go ahead, right, and then set the queue table to 0, discrete state plus action equal to 0. So what this is doing is, once we have reached our goal, now we don't want to have any stored queue values, so we can set all of that to 0. That's it. So no more having the queue values. So that way, we can make sure that we can have the queue table resetted after he reaches the goal. Hopefully that makes sense. Now what we are going to do essentially is we will set our discrete, so our discrete state will be equal to new discrete state. So this is the one which sort of updates and makes us take that action. This is somewhat the key thing. If we don't have that, we will not be updating our discrete state and no new actions would be taken, right? So we are setting our discrete state to the new discrete state. That means to say the present state becomes the new state. sorry, that means to say the new state becomes the present state, and then this keeps repeating. So we are trying to make the present state, equal to the new state. So the present state becomes the new state, and then again it loops through this, and the new state argmax, that means the new state actions would be taken, and everything would be just keep on updating as a okay. I think we can take this out, and we can just loop through our epochs, right? So sorry, episodes. I don't know why I'm so stuck with epochs. So for every episode in episodes, so what we are going to do, I would say in range of episodes, because we can't iterate through an integer value, right? So in range of episodes. So what we are essentially going to do is we are going to say discrete state is equal to get the state of that env dot reset, v dot reset, right? And then we just going to start performing that action, and then we can just say done equal to false, and we can just put this above and take it off, and then we have to give a tab. Yeah, I think now it is sensible. And what do we have redeclared? Yeah, so that's what. So what we are essentially doing here is we are trying to iterate through the episodes. So for every episode, right, in the range of the episode, so for every episode in the range of episodes, what we're going to do is we are going to get the state, and then we are going to do this basic logic, right? So that is what we're going to do. And and we'll not render for every we could render for the actions for every episode, but that'll make the agent figure out and exploit, figure out, explore and exploit all those things a little too slower. So what we're going to do is we are going to just print out for every, as initially we'll just start off, why not, we'll just initially we'll render everything, render, right, and then close this. Right, so this essentially what we're trying to do is we are trying to render after every, for every episode. Yeah, let's just go ahead and run the q learning file. Right, so you can see what is the agent is trying to do. And why not, let's just print the number of episode, so that we will know where exactly we are. So in the 4th episode, this just goes on, and maybe I've seen him to get it to work in maybe in the 200th episode, not really sure, but we just have to wait and see. At this point he's not even he's just going back and forth. This just goes to show as to how easily you can create a self-discovering, an agent who discovers himself in a given environment by giving the actions and with some basic algorithm. This is kind of crazy if you think about it. And also you can create your own environment where you could create your own environments, define all those variables and all those constants, and you can sort of get it working with your own environment. For the sake of it, I'm just going to fast forward this. Okay, so as you guys could see, it could not figure out even after 328 episodes. But nevertheless, we can make make it to figure it out a little more better in a much better way. Now here, essentially, what we are just doing is, you can think of it as we are trying to brute force it. So it's only trying to, the only objective for it is to just figure out, to go to reach to the, the final, the final goal. But what we could do is create some random actions, using epsilon. So let me talk about something called as epsilon. uh, Epsilon, you can think of it as like random moves. So as a agent learns to move in the environment, it moves from exploration to exploitation. So it makes sense, right? So when you are new to some kind of field, first you'll explore, and then when you're really good at it, then you start exploiting that field, right? So that is what I mean, that the agent moves from exploration to exploitation. So right now our model, our agent is just trying to figure out and to reach the goal, right? So and it's updating these q values, but these q values really don't, you know are not all that great, because it would not have explored anything. It would just exploit the, without even exploring, it's trying to exploit, so to say. It's somewhat trying to overfit. So we have to overcome that. So we can overcome that by, doing something called as epsilon decay. So what that essentially is it makes the agent take some random actions. uh, so it's sort of put some bias, right? It's trying to put some bias, so that the agent can also explore. So we are trying to brute force the exploration, rather than just making the agent exploit the environment without even exploring it. So we are trying to make the agent explore as well as exploit. So let's start. We will say epsilon ln equal to 1, and this is not a constant. This is going to be decayed, in the sense it's going to be reduced over time. So let's start. Let's have a starting epsilon value. Starting epsilon dk equal to, let's also keep it as 1, and end epsilon dk, and epsilon dk, we would say that it is the number of episodes, just randomly, divide, you know this double forward slash just returns the integer value. Suppose if this division returns a division, these double forward slash make sure it only returns the integer value. So that's our end epsilon decay. I hope it's still recording. Is it record? Okay, great, it's still recording. Okay, so end epsilon decay, and we would say, epsilon decay value is equal to epsilon, divided by the end epsilon decay minus the start epsilon decay. So that is the number of episodes divided by 2 minus 1 divided by the epsilon itself. So you can think of this as a very small value, which would start decaying as itself, for every iteration. So we can say, yeah, so what I'm going to do here is, while not done, and if, just random, right? So if np dot random is greater than epsilon, then I want the agent to take that particular the action if it's greater than epsilon. Else, let it just do some random action. Let the actions equal to np dot random dot randint from 0 to, or no need of all of that. We could just say env dot uh, action space dot sample. So what this would do is this would just give some random action. This would just perform from some random action. Okay, great. So the observation and all of that is great, so we are not going to change anything. I think we are just good to go now, and we just have to update our epsilon decay value. So what we are going to say is in within within the for loop, right? So if and epsilon decay is greater than or equal to the episode greater than or equal to the start epsilon decaying, then we can just update the epsilon, say epsilon is equal to or is minus equal to, which would say epsilon is equal to epsilon minus the epsilon decay value. And we're just going to close off the environment, and I think now it would make much better sense, and let's just run it. I think now the agent can sort of learn, and also just not exploiting, he can also explore, right? So that is what we are trying to do now. If I don't keep rendering this for every episode, it's going to become much faster. So as of now, I might speed up the playback so that you guys don't have to sit and watch all of this. Or as you can see, what I would do is I would just print after after every, uh, let's say maybe 2500 or maybe even 3000, I would say show every, so I'll say it as 3000, right? So what I'm going to do is I'll take this render off here, and I'm going to render it right here. So right, so if episode oops epi, so episode mod show every is equal to 0, then I'm going to say env dot render, so that way we will save some time and not uh, you get the idea. Just for the sake of it. So now I'm going to save it and I'm going to run it. See, now you can see, yeah, see how quick the episodes are running, right? So it definitely makes more sense to pause it for every, maybe we can see it for a less episodes as well. We can show it for every less than 3000, but why not? So, it closed in the sense that we were able to achieve it. No, I think the number of episodes got over, but he still wasn't able to. Maybe he got it, but maybe we missed it. So that is what is going on now. Okay, yeah. So in the next episode, we will talk about, or in the next tutorial, we will talk about, uh, the deep Q learning. So wherein we implement, deep, the neural networks as well, right? So that will be even more interesting. So see you in the next, guys.